Good morning.
Hello, everyone, and welcome to today's Middleton Group Masterclass session. Hope you are all doing well, and thanks again for joining us today. For those who are new to our presentations, Middleton Group is an Australian-owned and operated specialist electrical engineering organisation. We work across the power utility, renewable, rail, water, and heavy industrial sectors. Our organisation was founded with the sole purpose of working collaboratively with our clients to ensure successful and sustainable delivery of our projects. We are also firm believers in knowledge sharing, so that's why we are here today to share our knowledge with you. This week's presentation will be presented by none other than our technical director, Dr. Stephen Goh, who will be presenting on 22 kV AC traction systems. Stephen has 33 years of his rail experience, spanning across all modes of rail systems in all facets of design. He's a specialist in traction tower systems, such as 600 volts all the way to 1500 volts and 22 kV AC, of course. Stephen was also the traction tower and earthing and bonding design manager and lead on a $30 billion project across a project in the UK. The presentation today will run for approximately 20 to 25 minutes with 10 minutes remaining for questions at the end. Just some conference room housekeeping. If you have your microphones, if you could just put them on mute while the presentation is going on. If you have any questions, please feel free to post them in the chat and we'll get to them at the end during question time. If you have any super urgent questions, feel free to use the raise your hand feature in Zoom, but otherwise we can answer all questions at the end. And I will also post a short survey at the end just to know what everyone thought about the presentation and how we can bring you more interesting topics in the future. With that, I will hand over to Dr. Stephen Goh. Thanks, Stephen.
Thank you, Steve. Right. This presentation is an introduction to 25 kV AC systems. I will keep it at high level to benefit young engineers and project managers and all those who are beginners who are interested in 25 kV AC systems. Did you know that there's so many types of 25 kV AC systems? I had one person came up to me and he said, I thought 25 kV is 25 kV. Why are there so many different types? I didn't know there's so many different types. I'm going to introduce to you 4 types, which are commonly, 3 of them are very commonly installed, and also a 4th one, which is a static frequency converter, which is a relatively new technology. The simplest system is a rail return system. So where you have a source, 25 kV AC, feeding a train via the overhead line and returning via the running rails. And of course, there will be some leakage current. I'm going to introduce to you 2 terms for AC railway. I would call this a feeder station rather than substation. And the leakage current, not stray current. We reserve the word DC stray current for DC system. So this is a simpler system you can get. Of course, being simple, that means any leakage current, you have no control where the current is flowing. So it could be in somebody else's water pipe, gas pipe, or whatever, and you have no control. To improve on it, the booster transformer was introduced. Sorry, the not only is simple and leaky, and the electromagnetic compatibility is not quite as good. So the electromagnetic field, if you have any copper conductor or metallic pipe running along the railway, you will get an induced voltage. And to minimize that, so the booster transformer system was introduced. So you have a basically you install this booster transformer. One, the primary side is in series with the contact wire. There's a return side with a return conductor. So these are spaced at approximately 3.2 kilometers along the railway lines. And additionally, you have what is called a midpoint connector, connecting the running rails to the return conductors. The action of this booster transformer, it's rather special. So current going to the train will not flow, in theory, will not flow back to the source using the running rails. It will get pulled up the midpoint connector and flow along the other side of the transformer to balance the field here. So this is the benefit of the booster transformer. Of course, this is an ideal situation. So provided you don't saturate the transformer with DC current or whatever high current that you're drawing. So, and of course, if you have booster transformer failure, it will then give you very poor performance in the electromagnetic field cancellation. The idea is that you've got the return conductor very close to the contact wire to cancel the magnetic field. But if you have a booster transformer outage, that benefit is reduced or is not there. And of course, the auto transformer system was introduced. So instead of having the series connection of the booster transformer, these auto transformers are connected in shunt. So basically, you are transmitting power to the trains at 50 kV, but your train is still taking 25 kV between the contact wire, the plus 25 kV, and the rails, which is 0 volts in theory. And so the flow of the current is very different. So you can see that if this train is sitting between the two auto transformer, drawing 100% current, 50% of the current will flow in both directions, to the left and to the right. And if everything is working properly, you find that half that current here will flow upwards to join this current. So in practice, you only have half the current of the train is drawing, flowing back to the source. So here you have 25 kV and 25 kV, and that makes, and because you're earthing the center point, so you have plus 25 kV and minus 25 kV. So also because you're feeding the railway at 50 kV, that means you can feed a lot further, okay? Just to give you an appreciation of what each system would look like. So a rail return system would have the contact wire, catenary wires, and using the running rails as return. As an improvement, some systems have improved as install an earth wire, which are also bonded to the running rails, so that some of the currents, return current, will flow in the earth wire and cancelling the magnetic field of the contact wire and the catenary. I think I got my contact wire in the wrong place there. Anyway, the booster transformer will have a return conductor usually installed on the side here. These positions varies according to different installation. So just give you a rough idea where they normally sit. Now for the auto transformer and the contact wire and catenary are the same, so in the same position. And you have an additional wire which is got auto transformer feeder. Sometimes it's got negative feeder. The French got the negative feeder. The mine is 25 kV AC. So these two will be at plus 25 kV AC. And the earth wires are bonded to the running rail to carry return current. And on the right-hand side here, this is what is called the rigid overhead conductor bar. You may hear somebody else use the term conductor beam or some other term or conductor rail, but they're all just different names. So basically you have an aluminum bar is actually hollow inside, but a contact wire is clipped onto it. So the pantograph is actually making contact with a contact wire, not the aluminum. So together they can carry in excess of 3,000 amps, so which is ideal. So you have the insulator there and mounted to the soffit of the tunnel, yeah? The underside of the tunnel. Just for me to explain how one can design a 25 kV system, I'm going to use an example. So supposing you're asked to, you have received a document called Concept of Operation. And in there, you should be able to find all this information. You're asked to design a 25 kV system for a system in Melbourne or Sydney, because according to Australian Bureau of Statistics, by 2056, we will have 6.8 million people in Melbourne and 7 million in Sydney. So we are designing a system for the future, 50 years on or 100 years on, and that's why we're going for an 25 kV AC system and not DC system. So and normally you'll be looking at how many trains are you trying to support on this railway. 2.5 minutes headway, that means every 2.5 minutes there'll be a train in both direction, of course. And here I'm using an example of 10-car train. This is electric multiple units, which are much lighter than some of the trains are being built in Melbourne, which are high capacity metro trains, but they're actually twice as heavy as this train. This is actually a London Crossrail train, 10-car train, and this is for electric multiple units, very light. And supposing you're asked to, supposing you're told that this COO, we love acronyms in Australia, 1,500 passengers and normal loading, 4 persons per square meter standing, plus all the seats taken. And we normally use 75 kilograms per passenger to calculate the load of the passengers on top of the tear mass, which is the empty train mass. And in this example, I'm using 10 stations. So you're asked to design a system to meet the station-to-station runtime and end-to-end journey runtime, and you'll be given train characteristic for motoring and braking. If you haven't been given it, you may need to find out what sort of train size you need, what powertrain you need to do the journey time, achieve the journey time. So some of these parameters like acceleration of the train, 1 meter per second square or 1.1, commonly used in Australia, and 30-second dwell time. You may see that some of them might be 20, 25, and a very big station, it may go to 45 seconds or 60 seconds. And then you're usually given a maximum speed inside a tunnel. And in addition, you have to meet all the standards. Right. So supposing we are given a train characteristic, if we are given a train rating, that's fine. But if you don't have it, you will need to find out. You will need to go through an optioneering, go through, for example, 4 megawatt train, 4.5, 5, 5.5, and so on. and see which one will meet your journey time, meet the timetable. So the most important thing is your design must meet the timetable. If you can't deliver the timetable, you haven't achieved your objective. And of course, in addition, the railway must meet railway standard, must be safe, must be operable, must be maintainable. So all this must be taken into account. And of course, today, that's not quite enough. We want to make sure it is and its magnetic field is acceptable. And people are worried about exposing to magnetic field. Am I going to get cancer or leukemia? Although it is not proven, but the one that we most feared is people wearing pacemakers. Excuse me. So the high magnetic field may interfere with the pacemaker and causing malfunction. So all this need to be taken into account when you're designing a system, not just be able to run your train and meet timetable. And of course, in addition to that, you will have to look at the rail voltage, make sure that it's safe for the passenger to use, and also any leakage current to any DC railway that are running adjacent to it or at 90 degrees to it. And you will need to look at whether the 50 hertz current and its harmonics are going to be interfering with their track circuit, which are train detection system on the existing DC railway. So for this kind of system, you normally connect to a high voltage supply. In Sydney, we have 132 or 330. You can also connect to 66 kV if the supply is strong, but that's not preferable because it will introduce imbalance in the AC system, in the AC voltage. So, and called negative phase sequence, which is a measure of the degree of imbalance that you're causing the AC system when you connect your load. So I'm using a 25 kilometer long railway. This could be our Sydney Metro, if you wish. So 25 kilometer long. And if you're using a rail return system, and if the train is rated at 5.5 megawatts, it is very unlikely that you can feed from one end to the other. So you may need to use 2 feeding points to feed into the tunnel and have a neutral section between them. Why do we have a neutral section? Because we can't always guarantee that we're taking from the same phases. Here on the left-hand side here, I've shown that you're taking supply from A phase and B phase. On the other side, I'm taking B phase and C phase. So if we don't have a neutral section, it would go bang here. So that's why we need a neutral section, which is a dead section to segregate them. So obviously the train will have to stop at every station and in both directions. The voltage drop on the system, if I just show you half the system, it will drop virtually linearly. But of course, your design need to meet standards. So for a good system, you want to make sure that it meets the 19 kV permanent voltage. And of course, in addition to other like mean useful voltage that you need to meet as well, which is 22.5 kV, which is the average voltage. Conscious of time, let's boost the transformer system. So, and you can have a look at this and see whether this will perform better. Unfortunately, the word boost the transformer is actually misleading. You can see that the voltage drops at every booster transformer. So before long, you run out of voltage. So it's not boosting your voltage at all. It should have been called voltage depreciator. And again, the HV connection are very similar, but with the booster at 3.2 kilometers interval. And again, you need a neutral section. So if you're using booster to feed the supply of 5.5 megawatt train in a 24 train per hour per direction formation to meet your timetable, you will most certainly need to feed from both ends of the tunnel. Now, this is a big improvement because you're now feeding the railway with 50 kV. And these are auto transformers. So we normally have a pair. So if one goes out, one is outage, you can actually use one both. Some systems are designed so that they're actually in parallel already, they're tied together. And you find that some system, they might open the bus bars and feed from both directions. But of course, if the system is designed properly, you'll find that you should be able to feed from one end to the other. This is 25 kilometers long, and that will have the benefit of being able to utilize all your regenerative braking from the trains, so that regenerative braking energy can flow freely between the two sides of the system, past the neutral section. And this is just one way of creating a neutral section. There are other ways which I've come up with, that using rigid overhead conductor bar, you can actually create a switchable neutral section. So you keep all the switches closed for current flow through, but you need to open them. You just open the switches, then you're back to feeding from both ends. So that will be an improvement. And the voltage drop is, it was difficult for my my graduate to help me draw this curve. It's not easy to draw, and this is what you will see. It droops towards the next auto transformer station. These are auto transformer station, and then it droops again, and you keep doing it until you run out of voltage and you don't need to stand there anymore. So I'm using an auto transformer system. You're most likely to be able to feed from one end to the other and keep one of them as a hot standby. You can switch over within seconds if you get your system designed properly. Now, this is a relatively new system. It's very. Why do we use a static frequency converter? It has been used for a long time in the continental European countries, Sweden, Norway, Germany, Austria, and Switzerland. They used to convert HV supply grid system, some are 110 kV, some 132 kV, and 50 hertz, to 15 kV and 16 2/3, 16.7 hertz to feed the railway. So they use 1/3 of the frequency that we use in Australia and the UK. So in the UK and Australia, we don't change the frequency at all. It stays at 50 hertz. We're only using it to convert from 3-phase to 1-phase. So what are the key benefits? So if you do that, I've just got a little figure to show you here. You can connect it to a weak supply, 33 kV or 66 kV. But because you're taking supply from 3-phase, the load is balanced as far as the grid is concerned. You then convert that to DC and then DC to single phase AC to feed the railway. So because these are all power electronics equipment, you can actually make the output phases exactly in phase. So you eliminate the need for a neutral section between them. So it's just like DC. And it's except it's there 25,000 volts. So this is a rail return system, 25,000 volts. And power is equal to V times I. When the voltage goes up, your current goes down. So you minimize a lot of problems, including EMC problems and leakage current problems. So you can see no neutral section. So all the flickers and voltage dip when it goes for a neutral section goes out the window. And phase balances are not required because it's actually already balanced. Now this one has been installed in Queensland, and it is actually a greenfield site, Rothwell by General Electric equipment. So if you look at this picture here and this picture here, you can actually Google it, and you can see that the equipment it only occupies about 40 meters by 40 meters. The GE version, General Electric version, they come at 15 MVA. They're rated at 15 MVA. So if you want more, you have to connect them in parallel to get higher voltages. This is the ABB version. ABB uses 20 MVA. They come in 20 MVA units. And each one of these will set you back $1 million, Australian dollars. So if you need 40 MVA, then you need to couple them together, in parallel to give you 40. So where have they been used? So there are actually 7 units already installed in Queensland, Australia. 6 of them are actually rail return system, 1 times 25 kV. Only one of them by Horizon for the freight train is 2 times 25 kV AC on the output. So in the continent across there, lots and lots of units have been installed, and they're all 16 and 2/3 hertz, 15 kV. In the UK, 1 unit has been installed, might be 2 units, on the East Coast main line near Doncaster. So the original idea was to bring in 132 kV supply to feed the conventional feeder station. And in the end, someone realized that it may be cheaper to use static frequency converter, SFC. So they actually installed 2 units and 40 MVA. So it's got to be 2 times 20 MVA. So one feeds the new depot in the area, and one feeds the main line. And that lifted the voltage to allow the new Hitachi train to run happily across that section. So you can see it's dotted everywhere. And there are lots of them in Germany. If we were to use static frequency converter for the example that I've shown you earlier, you will, as a very minimum, you will need 3 units, spaced almost equally like this. So that means to operate the railway, you will most certainly need 2 of them running to be able to provide the service you require. If necessary, you can always add another unit, so which is quite handy. So whether you put it in here and here, or you double up on the same side, depending on whether you are able to get another independent HV supply or not for your N-1 redundancy. So on the railway side, if it's a 25 kV system, you don't change anything. It's the same, except that there are no neutral sections. I'm going to show you a couple of examples. I think we are running out of time. A couple of examples. And these are the AC system that Middleton group engineers have been working on. I personally have worked on all of them, and including 3 high-speed lines, Taiwan, California, Algerian, and UK high-speed one. But we don't have time to go through them. But I just show you a couple. What are the interface issues and the challenges? High-speed one. And because it's running cut through the countryside and across all the 750 volts DC railway, and there were lots of track circuits which are used to detect the presence or absence of a train, because they're using 50 hertz on the DC railway. Now this railway is 25 kV, 2 times 25 kV, 50 hertz. So of course, at every interface, we have to look at whether the 50 hertz current was sufficiently large to interfere with the 50 hertz track circuits and the other audio frequency track circuits. So normally in the UK, Network Rail will require you to look 2 kilometers in both directions to make sure that and all the track circuits are immunized. So if they are 50 hertz can be interfered with, you change them to either audio frequency, because you can make use of the tuning unit, just change the capacitor, and then you're off you go. And today you probably change it to exo counter. And so that's that one. And this is my latest one. Before I came to Australia, I lived in the UK for 31 years, predominantly in London. And this traction power system, I was the reference designer for this system. The price has gone up to $17 billion. Some said might be 18, and $34 billion Australian. So I was the lead traction power engineer and also the system-wide earthing and bonding for the central section of the Crossrail project. And I came up with the idea of 2 times 25 kV AC. My client's engineer said, "You're mad, that 2 times 25 kV AC for the metro system, that's normally used for high-speed train." I said, "Well, we have a high-capacity railway using a booster or rail return, and we need to have 2 feeder stations feeding into the tunnel when neutral section." When I show him the fireworks when he goes through the neutral section, and the safety chap said, no, I can't have that. So I had to look at the 2 times 25 kV AC system so that I can feed from one end, and I don't need a neutral section. So this system has no neutral section across rail. I introduced a number of innovation. This is the first system, metro system underground, that adopts 2 times 25 kV AC system using ROCB, rigid overhead conductor bar. And it is also the first system, metro system, that connect to the national grids of 400 kV supply, and allowing regenerative braking to the source. That was the first time as well. And other things like, and the system is very receptive to train regenerative braking. So it was so receptive that we can actually save 30% of the energy consumption, recycling the braking energy. And other systems, such as the earthing system, we're using the station foundation vertical bars to create use them as earth rods to create the earthing system. And because it's AC and it doesn't have the corrosive effects of DC, so we were able to do that. So these are just some of the innovation. This is the tons diameter was 6.2, and this is one of the stations, Farrington Station. And if you look at the tunnel itself, these are all the interfaces between different parties. So there are lots of different contractors working. They have the working you know, they have to work together to get things done. So the traction power system and earthing, system-wide earthing and bonding, we have to interface with all of them. So, and this is just a snapshot of the comms system installed on the wall. And this is a station platform. And that's it. So thank you for listening. This is Go Green, Go AT. AT is an auto transformer system. So that was my motto for London Crossrail project. Any questions?
Thanks a lot, Stephen. We've got plenty of questions in the chat already. So I might begin with just calling them out. So we got our first question from Dave Aston. Can a 25 kV traction system provide a high-speed rail link between Melbourne and Sydney?
Can we use a high-speed rail link? Well, we certainly can. And UK high-speed 2, I think the design speed is meant to be 400 kilometers per hour. It may not run at 400. Usually it gives it run at slightly lower speed. So no reason why we can't have a 350 kilometers per hour railway. The problem could be whether we have enough passengers to pay for it. So we'll have to be funded somehow, you know, some sort of a PPP and a project. Someone would design it and fund it and get it designed, built, and somehow to get the money back in one way or another. Yeah. I may be talking about that high speed in the near future as well.
Thanks, Stephen. Dave Aston again, which 25 kV AC system is typically in use with the high-speed electric trains as in Japan?
Almost all the high-speed ones, almost all of them, use 2 times 25 kV auto transformer systems. And with the exception of, which one was that? One of them in Spain, it may have been converted now. Originally, it was like a rail return system, but it was found that it's not so good because you can't use 50 kV to transmit power. So that means it's ineffective. So all high-speed trains will try and use 2 times 25 kV AT system.
Okay, great. And Mayor Puri, I think, yeah, he reaffirmed that it's 2 times 25 kV. And he had a question, how auto transformers just distribute current? Do we have regenerative braking also?
Yes. Today, when you design a system, you expect it to have regenerative braking capability. You want to maximize the amount of regenerative braking energy and recovery for it to be a very green system. And it will not be accepted if it's not allowed to do regenerative braking, because if we don't make use of the energy normally will be dissipated through a rheostatic braking resistor first, heating up the tunnel before you apply the mechanical brake or stand. So when you design it, make sure that the system is receptive at all times. So during the peak hours, it is easier because there are lots of trains, motoring train pulling off from train stations. They'll be demanding power. So when you have a train braking into another station, maybe on the adjacent track, on the opposite side of the track, and that would be very beneficial. So you interconnect them so the energy can be passed from the braking train to the motoring train. And auto transformer system will handle that quite efficiently.
Thanks, Stephen. We've got plenty more questions flowing through our chat. So next question from Mark Goodman. When designing a system, how do you accommodate the effects of track gradients when reviewing the train timetable, load, and regeneration from the EMU?
Right. You can't look at a design and you know whether it's a good system or not until you have done the modeling. The modeling part is very important. Multi-train simulation. Your multi-train simulation must have the alignment put into the model. You know, the gradient and the curves and everything. Usually mainline trains, the curves are not quite as bad as trams, but trams you certainly have to put in there. And because that is the second most power consuming exercise. Going up a gradient will be the worst. It uses up more power than when it's at grade. So a good simulation must have all the gradient, all this station drive time, and your tractive effort curves for high voltage, low voltage control all in your model, including regenerative braking to assess your system. So only when you have done that, then you can see whether some of this braking energy when trains are going downhill is being captured by a motoring train going uphill. So you should design it to maximize that energy.
Stephen, next question is from Navneet. I guess the question is, what is the diversity factor for calculation of demand?
You normally have to do N, which is everything is already in service. You also have to look at N-1. So if you have, for example, a feeder station normally have two transformer, one feeding east, one feeding west, for example. And when one is taken out, then the remaining one will now be T feeding. So you want to make sure that that unit can actually handle the load. And I would expect a system to be designed in such a way that under N and N-1, one piece of equipment outage will still provide a full service. So if it's N-2, then maybe you can go into a reduced service arrangement. But most countries that I've worked on around the world, they would expect N and N-1 to provide a full service. So that's that would take care of any diversity that you have. And also you want to make sure that if you are designing, say, 24 train per hour per direction, now how are you going to recover your timetable? You might have to run 30 train per hour per direction for, say, half an hour, for an hour, or 2 hours, depending on how much money you want to spend. And some system will accept even only 20 minutes. But 20 minutes, if your system is disrupted, you will not be able to recover that timetable. So these are the factors you've got to include in your system. Can you actually operate at 30 train per hour? Or can you provide a service, 50 years on? You don't want to be fixing the railway 50 years on, and let alone 100 years. 100 years time for AC railway, it may just be a minor improvement that you need, and it will work. For DC system, you certainly need a major upgrade to get there. AC system is less of a problem. So your recovery must be taken into account, and future service level must be taken into account when you design your system.
Thanks, Stephen. Next question is from Patrick. I think you might have answered this question in your previous answer. do we have to design 25 kV system for degraded modules similar to DC system? Example, N-1 scenario with a rectifier outage.
Yes, you do. When you run your train simulation, when you design a system, today you would use a multi-train simulation to help you. You can't just design it and expect it to work. So you design it and you simulate it. And when you have 2 units of maybe like auto transformer per site, you take one out to see whether it can handle the loading. So obviously now you have 1 unit is still supporting the same service. So its loading will go up. You want to make sure that it does not exceed its transformer rating.
Stephen, next question is from Cyrus. Do we have electrolysis issues in the AC system?
This is a very interesting question. I did quite a lot of research work on this. You see, unlike DC, when you have a leakage into, for example, where your train is, to a metallic pipe, and the current will flow towards the substation end of the pipe, and then it will try to return to substation because that's home. So when the current leaves the pipe to go into the soil, and the soil is actually your electrolyte. So that's where you have the chemical reaction and the corrosion. AC doesn't work quite like that. And AC, I've seen AC system, which is a much slower process in AC, AC corrosion. Not even sure whether you call it electrolysis, but AC corrosion. The one that I've seen is it almost like a pipe has got lots of dust on it. When you tap it, it just falls off. So the pipe actually gets slightly thinner, I suppose. So that sort of effect one tend to find, but it's over a long period compared with DC. So it's generally not an issue if you want to use the foundation of the station to create your earth grid.
Okay, thanks, Stephen, for that one. Next question is from Ashley. If an existing DC traction power system were to be converted to 25 kV AC, which of types of 25 kV AC system is best of choice? What are the considerations of such conversion?
Well, my favorite is actually the 225 kV AC railway, because you can put auto transformer along the track at normally there's space at 10-kilometer interval. If any particular location you have an issue, you can have the spacing reduced so that you have full control of any current that leaks into the ground and be pulled back by the auto transformer. So where you earth your center tap of the auto transformer is where the current will return from the ground. So by controlling that, you have full control of where your leakage current will flow. And if it's a rail return system, you don't have any control. Your 50 hertz current and also its harmonics may interfere with the DC railways, the track circuits and other systems. So, and also the new one, the static frequency converter, and you may want to consider that as well. Obviously, there are people with reservation with static frequency converter because it's relatively new. Not only that, it has a lot of power electronics in the front end converting from 3-phase to DC, and then from DC back to AC, single phase. So there's a lot of power electronics involved. And so any failure of that, and you may think that it doesn't work very well, And also, unlike a transformer-based systems, the devices which they use is called IGCT, in the integrated gate control thyristor, as opposed to IGBT. That when you go for this sort of system, if you want the system to, let's say, give you 30% overload, you have to specify and pay for it, because these devices will blow up if you overload them. So if you want them to carry 30% more, then you have to specify that I want you to put in a 30% bigger device that can carry more current. So that means your fault current is also controlled as well. So by switching off the gate signal, and you can control the fault current. So that is an advantage of a static frequency converter. And they are gradually getting their attention, but most people will still go for the conventional system. You know they're reliable, you know that they will do a good job over a long period of time, and you can count on them. Once the burning phase has gone and they're operational, they last for a long time without failure.
Thanks, Stephen. We've got more questions flowing through. Next question is from Navneet. Which type of OCS is used in the UK HSR1 and 2?
High-speed one is 2 times 25 kV AC. Originally, when they run from Waterloo station, it was actually 750 volt DC. And then, of course, when it joins the new section, which is 25 kV AC, it's actually 2 times 25 kV AC. I worked on that system too. And of course, when it was on DC, and every time it goes through a third rail gap, it causes a 50 hertz to occur. And all the 50 hertz track circuits were so unhappy, they have to increase it, the reaction time from 250 milliseconds to 1.5 seconds, in order that it doesn't think that it's malfunction, and it is the train causing it. But it definitely, you would go for 2 times 25 kV AC, and so is the high speed too.
Yeah. Okay, next question is from Shadman. What advantages do we see in an AC system over a DC system for a metro network? Is it worth converting in a brownfield environment?
I would say yes, it is worth converting, but it will cost money, a lot of disruption. You will have to do it in a controlled way, in stages. For example, I don't know how many of you would know, past the metro trains in Melbourne, and it draws an awful lot of DC current. So basically, it's reached the limit of our system, 1500 volt DC system, and the amount of current it draws, that it can create a DC magnetic field that will interfere with all the we call them sensitive receivers. These are MRI machine, transmission, electron microscope, and all the scanners or whatever it's on. So if you keep pushing it and draw more current to upgrade your system using DC, you will face this sort of problem. And you, at the end of the day, you may find that you actually have to cap the current, reduce the current, in order not to interfere with these sensitive receivers. In AC system, you don't have that sort of problem. It only produces a relatively small amount of DC. When, for example, when you start up with a transformer inrush, you get a bit of DC. And also in country where you have ice, then when pantograph is going through the icy pantograph, you get a bit of DC. But it's the 50 hertz that it produces, the 50 hertz magnetic field. But a magnetic field for human health, you can easily manage that because you allow 200 microtesla. And for example, London Crossrail, we can actually achieve 12 microtesla standing on a platform compared with 200 microtesla that you're permitted. So it's much easier to achieve human health as well as sensory receivers, meeting sensory receivers' immunity level.
Okay, thanks, Stephen. Next question is from Rico. So for SFC, will it be 1 times 25 kV or 2 times 25 kV system? Also to confirm, does it mean we expect less leakage current EMI issue for using SFC?
SFC, because you have to use more units than a rail return, the leakage current is reduced, but if using rail return for SFC, obviously the leakage current will be higher than if you use 2 times 25 kV. So the 1 times 25 kV went up with higher leakage current than 2 times 25, where you can actually pull your leakage current back to the auto transformer. And in the case of SFC rail return, you don't have that to pull it back. So you will have to design it in such a way that maybe you make sure that the rail to earth insulation is very good. Keep it clean if you were to adopt it. And also you will most probably need to use what is called dipole, or as we call it, just earth wire, additional earth wires in the soffit, probably in the 11 o'clock and 1 o'clock position. And then one at 7 o'clock position, you bond all 3 earth wire together and then bond them to the running rails. So the 2 earth wire, aerial earth wire, we cancel some of the magnetic field and give you a big improvement in your EMC performance. And one example is actually Heathrow Express Tunnel in London. And that is precisely how it was done. It was a rail return system. And they have 3 additional earth wires. 2 of them are aerial, not only to be used to earth the overhead contact wire arm that holds the wires, is also used to mitigate the EMF as well, electromagnetic field as well, to cancel the go current when you have the return current in the 2 earth wires.
Thanks, Stephen. Just conscious of time, I think we might need to wrap it up there. I know there's a few more questions in the chat, but I'm sure if anyone has any questions, you can reach out to Stephen via his email address, and he'd be happy to give you a bit more of an explanation. Or yes, feel free to contact us for any more questions. And I think we might actually need to do a part 2, Stephen, based on the popularity of your topic. So if we might just leave it there, given the time. So if I could just ask everyone if you could just fill out the survey. I've just dropped a survey link in the chat. Yeah, if you could just help us fill out that survey. With that, I think we might just wrap it up there. Thanks everyone for joining in today. And thanks again, Stephen.
Yeah, thank you very much.